Hi everyone. Today we will discuss Newton's laws of motion, and that is second law. In the previous video we had discussed the first law, so today we will discuss the second law. Now here if you consider this Newton's second law, so this says the change of motion is proportional to the motive force impressed. Means the change of motion is proportional to motive force impressed. When we say motive force impressed, that means the force applied on the object and is made in the direction of the right line in which that force is impressed. It means the motion will be in the same direction in which the force has been applied. Now the same thing, the same statement, it can also be represented, or it can also be narrated as the acceleration of an object is proportional to the net force exerted. The acceleration is proportional to the net force exerted on the object. So here, if the net force exerted, if it is, let us say, F, and mass of the object at which this force has been applied is m, then we have force F, it is equal to mass into acceleration. So you can see this force F is equal to mass into acceleration. M is the mass of the object, x is the acceleration, and force F, it is force applied on the object. So this statement says that the motive force impressed, and in this force which is applied and is made in the direction of the right line in which that force is impressed, means the movement, that is the acceleration, it will be in the same direction as the force has been applied. Now again, if you consider the statement corresponding to this, the acceleration of an object is proportional to the net force, means this acceleration A, it is proportional to the force applied. So here this relation, instead of writing this F is equal to m into A, we can write that F, it is proportional to this acceleration A. Let us say F is proportional to acceleration A, or acceleration is proportional to this F. So here, just to understand, suppose there is an object of mass m, okay, a force has been applied on this. Now it will move. From the Newton's second law, as soon as this force F has been applied on this mass m, it will move. So once it will move, so with what acceleration it will move? So it means that acceleration is proportional to that force. So here we can say F, it is proportional to this acceleration A. Now this proportionality, it can be replaced by a constant such that F, it is equal to mass into acceleration. So here this mass m, it becomes an proportionality constant. There is a relation between this force as well as the acceleration A. M is just an object. Okay, so there is a force, there is a relation between this force and A, and that relation is that acceleration is proportional to F, or F is proportional to this acceleration A. Now that proportionality can be replaced by a constant such that that constant is assigned a value m, and we say F, it is equal to m into A, and that m is nothing but the mass of the object. So here m, it is behaving as a proportionality constant, and we have this F is equal to mass into acceleration. Now here, instead of one force F, let us say various forces are applied. Suppose we have this mass m, and we have various forces, let us say F1, this F2, F3, and so on. So it means the summation of all forces. So here all these forces F1, F2, and F3, if they are applied in the same direction along the same line, then the summation or the resultant of all the forces, it will simply be F1 plus F2 plus F3 and so on, provided they are in the same direction, they are along the same line of application and all that. So F1 plus F2 plus F3, that will be equal to mass into the corresponding acceleration, and that's why here we see this force summation F, it is equal to mass into acceleration A. But all of us are aware that force is a vector quantity and acceleration is also a vector quantity. So just to get the clear picture of this, it can be represented as summation of force F, it is equal to mass into acceleration A. Now here, because forces always, they will not act along the same line of application, same direction. They can be experienced by the object m in different directions. Suppose you have this mass m, So force can be applied in this direction, let us say F1, force can be applied in this direction, force can be applied in this direction. So now in this case you can't say that the resultant of the force F, it is just equal to F1 plus F2 plus F3, because here we can't do this simple addition just because F1, F2, F3, they are not along the same line of application or along the same direction. They are along same different directions. Now force, it is a vector quantity, so using the vector concept we will have the resultant of the forces or the addition of the forces, and that's why here I have put this vector notation. So using concept of vector addition we will calculate the resultant of the forces applied on the object. Corresponding to that we will have this mass into acceleration A, and this acceleration A, it will be in the resultant direction of the force, resultant direction of all the forces. So this generalizes the Newton's second law, that the summation of force F, it is equal to mass into this acceleration A. I hope this is clear. Now, so here if you see this, the same thing here it is represented. The object's mass is proportionality factor, as I have just discussed. Force F, it is proportional to A, and this proportionality is replaced by constant, and that is M, such that F, it is equal to MA. So that is what it is representing here. The object's mass is proportionality factor between the net force exerted on the object and the object's acceleration, that is A. For a given net force, an object with larger mass, now you can see this, largest mass will have a smaller acceleration. So here if you consider this F, it is equal to M into A. Now if this M is larger, obviously acceleration will decrease. A will decrease as this M starts increasing, because we have A is equal to F upon this M, or F upon this small m. So acceleration A, F upon small m. As this m increases, the denominator increases, the acceleration will start decreasing. This is clear. So the acceleration will start decreasing. That the mass of an object is the property of the object which causes it to resist. So from here you can see, if m increases, acceleration decreases. That means what? M is behaving as a resistive object. This mass m, it is behaving as a resistive factor, because here it increases, acceleration decreases. If this m tends to infinity, if it becomes very large, acceleration A tends to 0. In that case you can say acceleration A tends to 0, and finally the object can come to rest. Or you are applying a force F on a very large object, and that object is not moving just because the force is not sufficient enough to cause movement to that object. So even if I try to push this wall, so if I push this wall, I am applying the force, but this wall is not getting pushed, it is not moving, it has not started moving. It means even though the force is applied, acceleration is 0. It means depending on how large it is, how fixed it is, what is the nature of that mass, so depending on that the acceleration will also depend. So in that case we say that larger the mass, smaller the acceleration. So from here we get all these type of concepts. So it means from this we can conclude that m is nothing, mass of the object is nothing, but it is a resistive factor. Now resistive factor we have also defined in the Newton's first law of motion, and that is called inertia. The meaning of that inertia we get from concept of inertia we get from Newton's first law, and that inertia means what? Resistance to a change. So inertia means resistance to a change, and mass also means resistance to a change. So combining both the terms like inertia and this mass m, we can conclude a new terminology, and that becomes the inertial mass. So here when we write this F, it is equal to m into A. So this m here attached with this equation F is equal to m into A, that will be termed as inertial mass, because that mass is having the tendency to resist the movement of the object. Inertia is also a feature to resist the movement of the object. So from there we get a new concept called the inertial mass, and that we get from this equation. F, it is equal to m into A. This m is termed as the inertial mass. Here if you write this equation, F is equal to m into G. G is the acceleration due to gravity. So this mass here m, it will be termed as the gravitational mass, because here it is not playing any role as far as the free fall motion is concerned. Just because of the acceleration due to gravity, this mass starts moving in the downward direction. It does not have its own property, it can't resist the movement, because G is here prominent. G tries to bring the object in the downward direction, it moves the object in the downward direction. So here F is equal to mg. So in this equation, this mass m, it will be termed as the gravitational mass. In this equation, F is equal to m into a, this will be termed as the inertial mass, because here this m is having the tendency to resist the movement, so we call it as the inertial mass. Here it does not have any tendency, because it is just falling under gravity. It is the gravitational pull which tends this object to move, such that we have F is equal to mg. So here in this case it will be termed as gravitational mass, in this case it will be termed as the inertial mass. Now here if you compare the Newton's first as well as the second law. So first law says what? The object will remain at rest till no external force is applied, or if it is moving, it will keep on moving till no external force is applied, and with this only we get the concept of the inertia. So here from second law we get summation of F is equal to ma. So if A is equal to 0, it means the summation of force F it is 0, or vice versa. If summation of F means the resultant of all the forces experienced by the object M, if it is 0, in that case also acceleration A is equal to 0. So 0 means what? The object is at rest, and that we get from the concept of the Newton's first law, that if no force is applied, the object will remain at rest. It will not change the state of motion. If it is in the rest position, it will remain in the rest position. So that's what we get. If no force is applied, or summation of all the forces experienced by the object or resultant of all the forces, if it is 0, it means the acceleration is 0. So in that case we can say Newton's second law or the first law, they are interpretation to each other. That way we can analyze. So, but from Newton's first law, we get the definition of what? The inertial frame. We get the definition of the inertial frame from the Newton's first law. So in that sense, we can say Newton's second law, it is completely different from Newton's first law. So these are the comparison that we can have as far as the Newton's first law statement or the Newton's second law statement is concerned. So these are the expression that we have already discussed. Now if you consider this comparison between the first law as well as the second law, similarly we are having the force magnitude is proportional to the acceleration magnitude that we have just discussed. So this law gives a connection between the unit of the force on one hand and the unit's mass and the acceleration on the other hand. Like this statement means that if you have F is equal to m into A, so this law gives a connection between the unit of the force. So from here you can calculate the unit of the force, mass into acceleration. So if you take mass in kg and acceleration as meter per second square, acceleration meter per second square, then F, suppose this is in kg, so 1 kg. Let us take mass as 1 kg and acceleration as 1 meter per second square. So 1 kg into 1 meter per second square. This concludes to what? 1. Force is equal to 1. 1 into 1, that becomes 1. So that 1 will have some unit, and that unit is termed as Newton. So this you can see here. So here you can see 1 kg meter per second square, and 1 kg meter per second square, that is termed as 1 Newton. So 1 kg into 1 meter per second square. So mass is 1 kg, acceleration is 1 meter square. It means the force, it will be equal to 1 Newton. This Newton unit, it is given with this scientist name Newton. So from there we get the concept of this Newton. Now the force F, it is also defined as the rate of change of momentum. The rate of change of momentum is force. So rate of change of momentum. So now again here we are getting a new concept, momentum. So rate of change of momentum, that is dP. If P is the momentum, then the rate of change of momentum, it will be dP upon this dt, and that is also F. So F, it is equal to dP upon dt. Now again, momentum is a vector quantity, force, it is a vector quantity. So just to generalize, we can write like this: F, it is equal to dP upon this dt. Now as far as the momentum P is concerned, it is defined as, it is a dynamic and a vector quantity. Momentum, it is a dynamic and a vector quantity, and if a mass is moving with the velocity v, then the momentum carried by that object, it is equal to m into v. So P, it is equal to m into this v. So that way we define this momentum. So here you can see this momentum, it is a dynamic and a vector quantity, and defined as P is equal to m into this v. Now rate of change of momentum. So at any point of time, suppose the velocity of the object is u, after some time it becomes v, mass of the object is suppose m. So change in momentum, it will be how much? mv minus mu. That means mv minus u. Again, velocity v or u, it is also vector quantity, so we can represent like this. So it is mv minus u. Now this change has taken place in certain time interval. Okay, so in that case you can say dp, it is equal to how much? dp, it is equal to mv minus this u. It has taken place in time interval, suppose dt. So dp upon this dt, that will be equal to this upon dt. So you can say it is m v minus u. Also in the differentiated form we can represent it as dv. So it is dv upon this dt. You can put this vector. dv upon dt is what? Acceleration a. So from there you get m into acceleration. So that's what we get here, m dv upon dt, and that is F is equal to mass into acceleration. So either you say rate of change of momentum is force, or summation of force F, it is equal to mass into acceleration. So that concept we get from here, F, it is equal to mass into acceleration. So these are the two different interpretation as far as the Newton's second law is concerned. There is another term called impulse. Impulse, it is nothing but the change in momentum. So change in momentum is termed as the impulse. So here mv minus u, you can say this is change in momentum, and that means that is impulse. Unit of this momentum, it will be what? Newton second. In Newton second, and impulse is again, it is not the absolute value of the momentum, but it is the change in momentum. It is not the rate of change of momentum, it becomes force, but change in momentum, it becomes impulse. So it is also a type of momentum. So unit will not change, it will remain same as the Newton second. So unit of impulse, it is Newton second. Unit of momentum also Newton second. Unit of force, it is Newton. Force, it is rate of change of momentum, and impulse is just change in momentum. So these are the terms that we get from Newton's second law. So after this we will discuss Newton's third law of motion, and then we will have lots of practice over problems based on laws of motion, that is first law, second law, as well as third law. Thank you.